us for the probability that a randomly selected housing unit has 2 or 3 rooms. 2 or 3 rooms. Okay. So we have. Oh. All right. Since they have that or right there, that or is going to turn into a plus sign. So anytime you see or, that means addition. You're going to add those two things together. Technically, we need to double check to make sure these things are disjoint. You can't have a housing unit that has both 2 rooms and 3 rooms at the same time. It has to be one or the other. So they are mutually exclusive or disjoint. So we can go ahead and look at their probabilities individually and then just add them together. So probability of 2, based on our chart, is going to be the 0.032, and then probability of 3 is going to be the same down here. About 12.5%.
On the homework, will it want it as a decimal or a percent?
Decimal. Yep, we'll always leave them with decimal. We'll have another example. The next example, I think, that we have, it's a percent. We want to change it to a decimal. So we never want to do any math with decimals because we can get a wrong answer, and we won't really see that so much until we get to chapter 6. But it's just good to get into the practice now of always making sure we have decimals, not percents. All right. So for part C, they ask us probability that it has 1, 2, or 3 rooms. I guess they write it out as 1 or 2 or 3. So this is going to be just an extension since it has the ors. Again, they're going to be turned into multiplication. And again, just the same reasoning we had up here, it can't have multiple numbers of rooms. So these are all going to be mutually exclusive. So these ors are going to turn into additions. So we get the probability of 1 plus the probability of 2 plus the probability of 3. 1, 0, 0, 3, 2, 0, 9, 3, and that is 0.135. Okay, so the addition rule says if you see an or, as long as they can't happen at the same time, and there's no overlap between the 2 events, you can just add those probabilities together. So, is there no eraser? So related to the addition rule is going to be the rule of complements, and this is the one we're going to use a lot when we get to chapter 6. It's going to be very helpful. So if we're looking at, first we have to define a complement, and then we'll talk about the rule. So if S is our sample space, so all the possible different outcomes that we can have, and E is an event, then the complement of E is going to be E with a little superscript of a capital C. In 105 it was an E with an apostrophe, but it means the same thing. They just use a C instead for complement. But it's the same thing, different notation. So this is E complement. It's going to be all of the different outcomes you have in your sample space that are not in E. So E complement is basically just like everything else. So if you're drawing a card and your event E is drawing a diamond, your complement would be drawing something that's not a diamond, so drawing a heart, a club, or a spade. So we're looking at just everything else that's not included. That's our complement. All right, so here's our complement rule. We've got this nice little setup with a Venn diagram. We've got here our sample space. We've got E, our circle right here is our event. Everything on the outside that's not included on E would technically be our E complement. So what we're gonna do when we calculate these, we have to have everything in our sample space. So if we have 100% of everything, and we subtract off the probability of E happening, what we're left with is the probability of E complement happening. So if there's like a 25% chance that E is gonna happen, then if you do 100% minus 25% and get 75%, there's a 75% chance that E is not gonna happen, which is E complement. That's kind of the idea behind it. But again, we're not using percents, we're gonna use decimals instead, just to make it a little bit easier when we get to chapter 6. So that's our complement rule. They write it like that, but let me, there's another way to write it, and they mean the same thing.